I had thought about deleting that mistake I just made, but I'm gonna leave it in there because and I'll actually be able to demonstrate. Remember, I said that we wanted the highest 8%, so I'll put the right value in here, which is 0.92. And I had already put in the 415 and the 17.3. We'll hit enter. And you can see we got 439.30. So remember that earlier when I accidentally put in 0.08, the value that we got out was around 390. And since we're looking for the highest 8%, that's going to be above the average. So, I knew I had to get something higher than 415. So when I got 390, and that's below the average, I knew something had to be wrong. So hopefully that followed that. And if not, by all means, ask me on Tuesday. Now, for the other question, which asked for the lowest 13%, this is something that should be below 415. So we'll go back to inverse normal. We'll put in 0.13. Go down to paste. And our value here is 395.51 square feet. Okay. Okay, so now the last thing with the normal distribution here is something called the standard normal distribution. The standard normal distribution used to be really, really important because the technology that I've been moving in and out of the screen was not readily available, and things had to be done with tables, the tables that I've told you basically to ignore. And we're going to use the calculator to do the work of the table. But to give you an idea here, again, I've drawn a normal curve. And if you remember the formula for a z-score, we talked about back in Chapter 4, remember it's x minus mu divided by sigma. So if we take a look at this curve, the center location is mu, and then we're jumping one standard deviation each time in each direction. So we've got two scales over here, x and z. And up here in the upper right-hand corner, I've given you two examples. If the value of x is equal to mu, then the corresponding value of z is going to be equal to mu minus mu divided by sigma, but that's 0. So on the z-scale, where we have x equals mu, the corresponding z value would be 0. Now, if x is equal to mu plus 2 sigma for two standard deviations above the mean, and we plug mu plus 2 sigma into the formula for z, the mu's are going to cancel. We're left with 2 sigma divided by sigma, and that's just 2. So we have a 2 right there. So the z-scale is basically telling you the number of standard deviations you are away from the mean in which direction. So on the negative side, to the left, we've got negative numbers of standard deviations away, and on the right side, we've got positive numbers of standard deviations away from the mean. Okay, so to give you an idea of where the standard normal still comes in, we've got 3 normal random variables here. Pardon me, w, x, and y. For w, the mean is 15, the standard deviation is 3. For x, the mean is 200, the standard deviation is 100. And for y, the mean is 40, and the standard deviation is 30. And I've asked you to do 3 probabilities here. If you haven't already looked at the commands, I would suggest, or even if you have, just make sure that you follow along and you can get the corresponding probabilities using the commands, the normal CDF commands on your calculator. And what you'll notice here is that when you plug them in, I wrote these out to 10 decimal places, which my calculator will give me. That's the most it will. And you'll notice that in every single case, these are equal to 10 decimal places. So why are they the same? This is not just luck. I planned it this way. So what I did down here is I've taken the values of w, x, and y, and I've calculated their corresponding z-scores using that same formula that we had up here, using the corresponding values of mu and sigma. You'll notice for w, the corresponding z values of w and are of 10.5 and 17.4 are negative 1.5 and 0.8. You'll also notice that for x, you also get negative 1.5 and 0.8, and the same is true for y. So in all three of these cases, what we were doing is calculating the probability that something falls between 1.5 standard deviations below the mean and 0.8 standard deviations above the mean. And that will be the same for any normal distribution, the same way that the empirical rule said that if we're within 1 standard deviation of either side of the mean, it's going to contain an area of approximately 68. It's going to contain approximately 68% of the data, or a probability of approximately 0.68. And sure enough, if we convert to that z-scale with a mean of 0 and a standard deviation of 1, if we plug in via the normal CDF and we use the z values of negative 1.5 and 0.8, we get the same value that we did in the cases of the probabilities for w, x, and y. Okay, similarly, if we're using z with normal percentiles, if we go back to the paint question, the lowest 13%, the highest 8%, there are the values, the inverse normal, but instead of having the 415 and the 17.3, we put in 0 and 1, and we get those values right there. So what we're getting with the inverse normal are z-scores. And what this tells us is that for any normal distribution, the cutoff for the lowest 13% will always occur at 1.126 standard deviations below the mean. The cutoff for the highest 8% will always occur at 1.405 standard deviations above the mean. Okay, the last page is a problem for you to try. I've given you the answers down at the bottom, and you'll use the normal CDF and inverse normal functions. So please make sure that you can get those. And sorry it took a little while longer than I thought to get this up on YouTube, but it should be good to go now. And I will be on Tuesday. Look forward to seeing you then. Bye.